This video is the beginning of Chapter 12, and Chapter 12 is about intermolecular forces and phase changes. Most textbooks call it about liquids, but honestly they don't really focus just on liquids, so we're going to talk about all the phases together. Presumably, depending on who you had, at the end of Chem 1, one of the last chapters you probably talked about was gas laws. This one kind of fills in the rest of the gaps, liquids and solids. Okay. But first we need to talk about intermolecular forces. So in Chem 1, we talked about how bonds are formed, how atoms are stuck together. What intermolecular forces is talking about is when you have multiple molecules or atoms, things that are not bonded together, how are they going to interact? Are they going to repel each other? Are they going to hold together? How's that work? Okay. There are a few different intermolecular forces, and I need you to understand the basics of how each one works. Okay. The first and the most obvious and the strongest, it's a relative measurement here, is something called dipole forces. So this is the first one we're going to talk about. Okay. This only applies to polar molecules. If you don't remember how polarity works, on OnCourse I've posted a list of all my videos from last semester. One of the later ones in that playlist is one about polarity. I'm going to recommend you watch it. I might actually put it back in this section. But the idea is a polar molecule is something that has an uneven distribution of electron density. So it's slightly positive on one side, slightly negative on the other. I'm going to talk about this in very broad terms. So what we mean here is, suppose you've got some molecule. I'm just drawing it as a blob. And the idea is one side of this molecule is somewhat negative and one side is somewhat positive. It doesn't have to be full negatives and full positives. It could be partial negatives, partial positives, good enough. But the idea is if you have a bunch of these laying around, they are going to line themselves up because negative attracts to positive and negative repels negative and positive repels positive. They're going to line themselves up so that they end up forming this type of thing. I didn't draw them all the same size, but that's just because I can't draw. And so positive is attracted to negative, and it doesn't form a bond, but there is an attraction here between the different parts of the molecule. So visualize it just like magnets. It's literally the same concept as magnets. If you have a positive side and a negative side, if you throw a bunch of magnets in a pile, the positive's going to find the negative, they're going to lock together, and the positive's going to find negative, and they're going to lock together. Okay, there's not going to be a physical, not like melted together or welded together. They just are attracted to each other. It's literally the same concept. Okay, the more polar the molecule is, the stronger this force is going to be. And polarity is there's like completely nonpolar and there's completely ionic. Polarity is the gray scale in the middle. So there's a lot of range in how polar something is. Okay, this is a relatively strong force. So what this tells us is that if we have polar molecules, they're going to hold together. One molecule is going to hold itself to the other molecule fairly strongly. Okay, pretty straightforward. This is one of the easiest ones to understand. Okay. The next force is a little weird. It also has a weird name. It just doesn't feel right. But that's okay. So, this one is called Induced Dipole Forces. So basically this is how polar and nonpolar molecules interact. And we know that polar and nonpolar don't mix very well, so we would expect this to be a pretty weak force. So this is polar and nonpolar molecules interacting. Okay, so a polar molecule I'm going to draw just like we did up here. We have a negative, definitely a positive and a negative here. And nonpolar, I'm going to draw as like amorphous blobs. Basically, there isn't a definite positive or negative. That's what nonpolar means, is everything's evenly distributed. Okay, so this one is polar, this one is non-polar. So what we see is that this non-polar one, the electrons are evenly distributed. And even though they are used in bonds, and even though they are either bonds or lone pairs, as we saw with Lewis structures, they are evenly distributed. But what happens here is if these things get close to each other, they're still electrons, and they're still going to behave like electrons. So if they end up near the positive side, they're going to be attracted to it. So the electrons are inherently going to kind of move this way. Not all of them. It's not like all of them are going to abandon ship and move over to this side, but they're going to spend more time on this side of the molecule. Okay, and this leads to the polar molecule is still polar. I apparently can't draw consistently, but that's okay. And what we end up with is something, I drew it bigger this time, sorry, is that the electrons are spending more time on the left, so they would be partially negative and partially positive. This one has not changed, it's still polar. This is now what's called an induced dipole. It wasn't polar to begin with, but the electrons have gotten moved around to the point where it is slightly polar. Oops, induced dipole. Okay, so what we're looking at is the interaction between these two things. This is a really weak force. And this makes perfect sense because we don't expect polar and non-polar molecules to interact very well. They just don't. Okay, this is a very, I'm going to go ahead and put very weak force. Okay, so, but this is how it works, is basically if there's polarity is going to affect even non-polar molecules to some degree. Okay. The third one we're going to talk about are called London dispersion forces. There is kind of a trend over the past maybe 10 years of chemistry where some textbooks call it dispersion forces and some call it London dispersion forces. So I'm going to put the London part in parentheses. London was some guy's last name. Yes, it's the name of a city, but this has nothing to do with the city per se. London dispersion forces. So a lot of times I'm just going to refer to it as dispersion forces, but some textbooks or maybe the sapling homework might refer to it as London dispersion forces. They're the same thing. This is how non-polar molecules interact with each other. Okay. This one feels a little like the last one, but it seems almost completely random. Okay. So what happens here is you have non-polar molecules, which I'm just going to draw as amorphous blobs like I did the last time. So this is non-polar. This is non-polar. Because I'm being inconsistent about whether I'm hyphenating it, I'm not sure what the right answer is. Okay. What happens is, even though these electrons are evenly distributed on either one of these, it is entirely possible, because electrons are really, really small and they're moving at near the speed of light, even if they're in bonds or in lone pairs, that they're moving around. The odds of them being completely evenly distributed all the time is not very high. Okay, so what happens is, at some point, one of these two, I'm just going to pick the left one, it's entirely possible that the electrons just won't be evenly distributed. The electrons there might be more of them on the left than on the right or something. Okay, so what we end up with is this thing called an instantaneous dipole. And what this means is basically, for a brief moment, the electrons are unevenly distributed. I'll try to write that in here. So for a brief moment, the electron distribution is uneven. Okay? And what happens is, if this isn't near any other molecules, it'll literally just go back to being nonpolar. They'll just spread back out. But if they happen to be in the contact with another nonpolar molecule, which honestly, if you have like a big container or even, you know, a small container or whatever, I mean, there's trillions and trillions and whatever of any of these things, just because there's the sheer number of them, statistically, even though this is very unlikely, it's not impossible. And if it happens once, what happens is essentially the same thing that we saw here, is that if you have an uneven distribution and you put it near a nonpolar molecule, the electrons will shift over to one side to compensate. That's what's going to happen here. Because there is a slight positive here, the electrons are going to move in that direction. Okay, I don't know how many electrons are going to move, I just happen to do 2. Okay, and what happens is that basically this now becomes partially polar and it reinforces the first one. Eating up a whole page for this, I guess. So this was instantaneous dipole, really unstable, may not last very long, but this one also formed a dipole. This is an induced dipole, and it helps reinforce the first one. And now if there's 2 of them and there's other ones, they'll all fall in line really easily. So this seems like this should be a weaker force than this. And in some ways it is, and in some ways it isn't. Each individual force probably is weaker because neither of these really were polar ever at any given point. They're just kind of partially polar. But the main limiting factor on this is that polar and nonpolar molecules don't mix together well. So this would be like if you had oil and water and you had like the water on the bottom and the oil on top. This is only going to happen at that interface where the 2 interact. So you're going to get limited interaction. So overall, adding it all together is not going to be a very important force in how this thing holds together. This, if you had a container just full of the oil or just full of some sort of like hydrocarbon or nonpolar molecule, there are going to be so many of these that the force is going to add up. So this is a weak force, but it adds up. Okay. So we talked about with polar molecules how the force in between things is going to be stronger depending on how polar things are. There's another, these are non-polar, so we can't use polarity to judge whether or not this is going to happen. So we need to talk about something called polarizability. Basically, how likely is it to develop one of these spontaneous dipoles? Okay. So this is I guess I'll write it all out here. It's a measure of how easily a nonpolar molecule can develop an instantaneous dipole. So in other words, this entire thing is based off the idea that nonpolar molecules just randomly form an instantaneous dipole. How strong this force is mostly has to do with how likely is this to happen. Okay. In general, so one of my college professors, she explained it like this. What we need is essentially these electrons to be able to move around. The more likely they are to move around, and the farther apart they can get, the farther this negative and positive can get, the more likely this is to exist. Okay? So, in other words, the simpler answer of how this works is the larger and floppier a molecule is, the more polarizable it'll be. So let's look at an example, and then we'll probably end this video even though I'm not quite done with intermolecular forces. That's okay. We're going to look at the halogens on the periodic table. So fluorine, chlorine, bromine, iodine. These are all completely nonpolar. They all are also diatomic. So this would be F2, Cl2, Br2, I2. We're not going to care about astatine. Okay. But they all kind of do similar things. So it's an easy thing. They're similar enough that we can compare them easily. Okay. So what we find is that for something like F2, diatomic, it's a gas, okay? It's a very small, it's also very non-polar because it is small. So what this means is this is not polarizable. I mean, it's not that it can't be, but it's really unlikely to do so. So what this means is this thing is going to have very weak forces between the two. Like if you had an F2 here and an F2 here, the interactions between them are going to be very, very small because neither of them can get that uneven distribution. Because it's so small, as soon as they start to separate, they'll come back together. And what we see is very weak dispersion forces. So the consequences of that is there's not a whole lot holding them together, and the consequence of that is that it's going to exist as a gas. Okay, Cl2 is also small. It's a little bit larger, but it's still small. It's pretty non-polar. It's, let's put moderately polarizable. So what we see is that it also has somewhat weaker dispersion forces. And it is also a gas. Going up the food chain here, bromine is larger than either of those, which makes it more polarizable, which means stronger forces, which means it actually exists as a liquid at room temperature because the forces holding it together are just a little bit stronger so that it can't break apart and bounce around like gases. They have to the forces are holding them together so they move across each other, but they're not rigid. They're liquids, so they move like that. Iodine is huge compared to the other ones, which makes it very polarizable for a non-polar molecule. And this one actually exists as a solid. So within this trend, in the periodic table, these all form diatomic molecules. They all essentially behave the same. But we have really, really light gas, slightly denser gas, liquid, solid. And the only difference between these is size. This is really, really small, so it's going to have very weak forces. It's going to pop apart. This is a little bit more polarizable. It's a little bigger, so it's a gas, but they hold together. They're a little more dense. Bromine is getting bigger, so it can be more easily separate the positives and negatives, so they're going to hold together better and will be a liquid. Iodine is a huge molecule, and so what happens is the positive and negatives get very separated and allows for a very strong dispersion force, and these things are going to exist as a solid. They actually exist as like these really pretty purple crystals. So a little complicated, a little dense. We're not quite done with intermolecular forces, but the next video we should easily finish it. All right, thank you.